Hello again, and welcome to Advanced Physics for High School students. This is Lesson 46, and it is entitled The First Law of Thermodynamics. This is a fairly long and complex lesson, but it lays the groundwork for understanding some important concepts in thermodynamics, so it merits the attention that we give it. The better you follow and grasp the ideas now, the easier it will be to apply the ideas in later lessons. So I encourage you to invest your time well early on to reap the dividends that investment will pay in the future. You'll recall that in one of the very first lessons of this course, we stated that physics is the science of energy and its conversions. So far in this course, we've described kinetic energy, gravitational potential energy, and elastic potential energy, the three kinds of mechanical energy. We've defined heat as thermal energy that moves from one body to another as a result of temperature differences. We've mentioned that thermal energy, something that we've called internal energy, is the kinetic energy of the random motions of all the particles contained in a substance. We've even written an equation for the internal energy of an ideal gas, and we'll remind ourselves of this equation in a few minutes. We've discussed the concept of work, writing an equation for work that a force does when it moves an object through a distance. We've hinted at electrical potential energy that electrical charges possess when they find themselves in the presence of an electric field. Because some of these energies are easier to produce and harvest, whereas other types of energies are actually more useful to us, it's important for us to be able to convert between types of energies so that we can exploit the benefits of each type. It is possible to convert all of these energies, and others that we'll study in later lessons, into other types of energy. Nature gives us some ground rules governing the conversion process, and we'll learn that there are some consequences to these conversions. The name given to the branch of physics that studies these conversions is sometimes referred to as thermodynamics. If you look in the McGraw-Hill Dictionary of Scientific and Technical Terms, you'll get this definition of thermodynamics. It is the branch of physics which seeks to derive from a few basic postulates relationships between the properties of matter, especially those which are affected by changes in temperature, and a description of the conversion of energy from one form to another. One of the most influential inventions of the modern era is the heat engine, which is a machine for converting thermal energy into mechanical energy. One significant type of heat engine is the internal combustion engine, such as these pictured here, a small engine on the left, perhaps like you would see on a lawnmower, or an automobile engine, such as the one that's on the right. These are ubiquitous in developed societies, found under the hood of every automobile. The internal combustion engine makes your commute around local and distant geography quite a bit easier than it would have been 150 years ago. You also find internal combustion engines in a wide array of power tools, from lawnmowers and weed eaters to portable electric generators and chainsaws. Just about any machine burning gasoline or diesel fuel contains an internal combustion engine. And today we begin to study what governs the energy conversion processes in these or in any type of engine. We begin by taking up the first law of thermodynamics. Historically, our understanding of heat and thermodynamics resulted from attempts to understand and improve steam engines, such as these seen here. The Chattanooga Choo Choo has a steam engine in its backyard, or some plants have them in large buildings. During the Industrial Revolution, people didn't start with an appreciation of physics and then build the machines. The machines came first, and folks tinkered with them, trying to learn what was going on. James Watt is credited with improving the steam engine, and the MKS unit for power is named in his honor. Here are some of the key ideas resulting from that study. Some key ideas in thermodynamics. The first is that heat is the spontaneous flow of energy from regions of high temperature to regions of low temperature. So suppose you have two objects touching each other, one of them at a high temperature and another at a low temperature. Both of them possess thermal energy, but the particles of the higher temperature substance are, on average, moving faster with more kinetic energy than the particles of the lower temperature substance. As a result, thermal energy will move naturally from higher temperature objects to lower temperature objects, and we call this energy in motion by the name heat. Next, number two, Gases are made of small particles, and increasing the temperature of the gas causes an increase in the average kinetic energy of the particles of the gas. So, when a gas is heated, then energy is transferred to the particles of the gas, and the particles move faster. This diagram shows a container that has a few gas particles in it, the arrows representing their instantaneous velocity at some point in time. Now, if I take a flame and I heat this gas, then what ends up happening is that the particles of the gas have more kinetic energy, so they would move with faster speeds the hotter and hotter the gas becomes. The faster the particles move, the more kinetic energy they have. You'll recall that the absolute temperature of a substance is a measure of the average kinetic energy of the particles of a substance. In fact, that's the definition of absolute temperature. A third idea is this: work can change an object's temperature. For example, rubbing your hands together makes them feel warmer. Historically, the idea of heat energy, which was measured in calories, like Q equals mc delta T, evolved separately from the idea of mechanical energy, which was measured in joules. Remember, mechanical energy, work, is force times distance? Near the end of the 18th century, the conventional wisdom was that heat was an invisible, massless fluid called caloric, from which we get our term calorie, and the connection between heat and work was first noticed by an American, Benjamin Thompson, later called Count Rumford by the Germans. Thompson worked in an arsenal where a large drill was used to bore out cannons. Water was poured over the cannon while it was drilled to cool the equipment, and Thompson derived an experiment using a blunt drill and a cannon immersed in water to demonstrate that the action of the friction could eventually boil the water. Thompson claimed it was the action of friction instead of the flowing of this theoretical caloric fluid that produced a rise in the temperature of the water, because there was a seemingly infinite amount of heat produced by this rubbing action as long as you kept turning the cannon against the blunt drill. About 50 years later, James Prescott Joule, an English physicist, actually built a sensitive water-holding instrument with paddle wheels and falling weights to measure the conversion of mechanical work into heat, giving us our present-day equivalent between the two. 1 calorie is equal to about 4.2 joules. In this course, you'll work mostly in joules, though you ought to be familiar with both sets of units. A calorie, by the way, is the quantity of heat that, when added to 1 gram of water, raises the water's temperature by 1 centigrade degree. A fourth important idea in thermodynamics is the idea of internal energy. Internal energy, U, is the sum total of all the kinetic energy of all the particles of a substance. So let's suppose, for example, I had a closed container with 10 gas particles. The particles are moving randomly with various speeds. The particles interact with each other only by bouncing. They interact with the walls of the container by bouncing off the walls. Suppose that particle number 1 has a speed of v1, and particle number 2 has a speed of v2, and particle number 3 has a speed of v3, and so forth all the way through particle number 10 with a speed of v10. The kinetic energy of the ith particle is going to be given by 1/2 mvi squared. We're assuming all of these particles are identical. So the total kinetic energy of the particles in the container is given by 1/2 mv1 squared plus 1/2 mv2 squared plus 1/2 mv3 squared, so forth all the way through particle 10, 1/2 mv10 squared. If I know what all those kinetic energies are, then I could come up with an expression for the internal energy of the gas by adding up all those energies together. That's a complicated expression. In general, our gases will have many more than 10 particles. Our gases will have more like Avogadro's number of particles. But whatever that number is, if I were to add up all the energies, then we could say that there is a total energy of the gas. The sum total of all the kinetic energies of all the gas particles, and that number is what we call the internal energy of the gas. Now that we've set down these 4 basic ideas of thermodynamics, let's move on to developing some of the important thermodynamic equations. We start with an equation that I'm just going to give you from kinetic theory. That equation is that the internal energy of a gas, U, is equal to 3/2 nRT. where U is the internal energy of the gas, N is the number of moles of the gas, R is the ideal gas constant equal to 8.31 joules per mole Kelvin. That number will be different if you have a different set of units, so pay attention to that. And T is the gas's absolute temperature. Because it's beyond the scope of this course, I'm not going to tell you how we get this equation, except to say that it results from attempts to relate the mechanical energy of the randomly moving, bouncing gas particles to the absolute temperature of the gas. Now, we're going to do a little calculus. Those of you not taking calculus can cover your ears for a moment. We're going to differentiate this equation and then rearrange it slightly and then express the equation in terms of a delta notation. And it's that delta notation equation that's going to be important to us. So here we go. Let's differentiate the internal energy with respect to the absolute temperature, du dt. Because 3/2 is a constant, and n is a constant, and r is a constant, then when I take du dt, then I get 3/2 times n times r. Now, let's take that equation and multiply both sides by dt. Now that ends the calculus part, so you non-calculus students can uncover your ears now. Let's take these differentials, these d's, and turn them into deltas, because that's going to be how you use them in this course and on the AP exam. And now we end up with delta U is equal to 3/2 times N times R times delta T. This is the final equation that you have to remember. This is the equation that we saw way back in an earlier lesson. The change in internal energy of a gas is 3/2 NR delta T. What this says is that if the temperature of an ideal gas changes, then the ideal gas's internal energy also changes, and how it changes is given by this equation. That is not the only way that internal energy of a gas can change, but it is one way. Numerically, if I know what the numbers are that are involved, then I can calculate the change in the internal energy of the gas. Now, as an aside, this expression is only good for ideal gases. It's not good for gases that have structure, say like diatomic gases such as nitrogen and oxygen, or gases with different particles such as water, which is made of hydrogen and oxygen. These more complex gases can have contributions to the internal energy due to vibrations and rotations of the gas molecules. But we're not going to be asked about that on the AP exam or in this course at this level of study. So we're going to take this equation, the boxed equation, and run with it. This is one of the important equations of this lesson.